This is a brief but very important video on the chemical and physical speciation of the elements. And so it's very important to think about elements in terms of their speciation, meaning what form are they in? What form they are in is important with respect to biology, whether it's a nutrient or available, or if it's toxic. Just knowing what and how much of an element is present tells you very little about the bioavailability and toxicity of that specific element. And so let's just go through and look at how we can start to figure out the different forms of an element. So first off, I think it's important to look at the physical speciation of an element. And so when I mean physical, we're talking about the size of the particle in which it's associated with. So let's start on the large scale side in terms of elements associated with rocks or just big debris or fish, very large particles. We'll keep that term particles. But as we go to smaller and smaller size fractions, say 1 millimeter, now we're looking at small animals like zooplankton or gravel, and then we start getting into clays and sands or diatoms, small algae. Coastal diatoms are about 100 micron, while the diatoms in the ocean are much smaller at 10. And then we approach the 1 micron size, a millionth of a meter, and now we're starting to think about bacteria. Remember, all of these particles, no matter if they're inorganic or an organism, they contain elements. And so it's at this division here at either 0.2 or 0.4 where scientists have decided that is the difference between a particle and something that is dissolved. So remember when we talked about weathering, we had the dissolved solids and the suspended solids. So this is the division between suspended and dissolved. So biologists, and actually I think this division is actually becoming more common, is they say that anything above 0.2 microns is a particle. Anything smaller than 0.2 microns is dissolved. Now, chemists and EPA, they still use the division of 0.4 microns. And I'll explain why that's so. So the 0.4 microns is the old definition, and it has validity in that if you are a spherical particle with a 0.4 micron diameter in water, you are large enough that gravity will act upon you and actually settle you out. You will not stay suspended within that solution. And so that's where the 0.4 micron cutoff came to be. But we would say that all bacteria are particles. They're not dissolved, they're particles. And so what happens when you run, say, your water sample through a filter is that some bacteria aren't spherical. They have odd shapes. They might be, oval shaped. And so in that case, the bacteria could actually get through the filter and be counted as dissolved based upon its shape. And so by using a 0.2 micron filter and this cutoff, we will assure that all the bacteria get counted as being particles, particulate, and not dissolved. So once we go into the dissolved phase, then we start looking at viruses, things like colloids, which are very common in all solutions. These are particles that are so small that they stay suspended. For example, milk. Milk is opaque because it is actually a colloidal suspension where the proteins and all the molecules, macromolecules in milk are so small that they stay suspended and do not settle out. And as we get to smaller and smaller sizes, we start getting into what we call soluble or truly dissolved. These are essentially molecules, and they're that small, and they stay in the dissolved phase. So when we look at, say, iron as an example, we could see that iron in the particulate form, at larger size fractions, we could see them associated with clays. We could see them associated with, say, diatoms, with different sorts of organisms that are on the size of 1 to 10 micron, or maybe even just a piece of organic matter, which called detritus. But then once we get beyond the cutoff of 0.2 or 0.4, we then start to see iron associated with more like molecules, like humic acids, or just as a very small mineral colloid. And then again, as we go further, we could look and see, say, an iron wrapped up, chelated by a siderophore, or a part of, say, a heme complex. This would come from biology. A heme complex is something that's very common in biology. Hemoglobin is a good example, but iron fits very nicely within this complex. And then we get into the truly dissolved, where we're just talking about iron as a molecule within the water. So last, I want to just talk a little bit more about chemical speciation and what it means. So chemical speciation, again, it's very important to think in terms of speciation because it's the distribution of the element in all the different chemical forms that the element could have. And so this chemical speciation will depend upon what type of matrix we're dealing with. And in terms of matrix, in natural systems, I'm just talking about the different types of environments in which the element can be present. And so really briefly, I just want to run through a few examples. Say cadmium. Cadmium is one of my favorite elements. It behaves like a nutrient in ocean distributions. And in the ocean, we can see that it is usually associated with chloride, which makes sense. There's a lot of chloride in seawater. It can also be bound to organic ligands. But in river water, it's usually just in the hydrated form or bound to organic ligands. Mercury, similar. There's lots of chloride present in seawater, so that's the form in which it takes. It can also be methylized, and so methylmercury is a dangerous type of mercury that is found in fish, and it's very, very toxic to humans because it is an organic form of mercury. So when you uptake something like methylmercury, it will easily go into your cells, go into your brain, and do damage. An inorganic form, such as mercury chloride would be less toxic to your body. It would potentially pass through your body or be sequestered by mechanisms within your own body to detoxify the mercury. And again, we see that in seawater and river water that mercury does form different species. Another example, uranium. It's primarily found in a carbonate form in seawater. And I could go on and on with examples, but some elements such as arsenic, it depends upon the oxidation state. And it's similar in both seawater and river water, but again, depending upon the oxidation state, it will have a different form or different speciation. So again, these are just examples. We could go on and on, but again, the point here is that the species really defines, say, how toxic it is in the environment or to a living organism, or how inert and not important with respect to biology and its ability to be taken up. So one last example I'll leave you with is something like chromium, where chromium-3 is an actual micronutrient to many organisms, while chromium-6 is actually a carcinogen. So if you were to measure how much chromium is in a sample, that really doesn't tell you much about how toxic or good it is for an organism. It really depends upon the speciation. So you would need to measure and use analyses that helps you determine what oxidation state you're dealing with. So with this video, we're going to take this idea of speciation and go into the estuaries and into the oceans to figure out how speciation is changing within those environments.